Friends, in today's video, we are going to see the steady flow processes and the first law for such steady flow processes. We discussed about steady flow processes in our earlier lecture, where we said that a steady flow process is the one where we have the control volume in which the mass and energy is constant. That means changes in mass with respect to time is 0, changes in energy with respect to time is 0. However, we can have differences in other properties, like here as I mentioned here in the temperature, that with time the temperature is remaining constant, however within the space the temperatures are different. So this is termed as a steady flow process. Now in industry, there are so many steady flow processes which are taking place, like turbine, pumps, boiler, condenser, heat exchangers, and if you want to make energy balance across them, we need to write the equations associated with that. Now as we know that for performing an energy balance, first we need to perform a mass balance. So there is an open system, there is a control volume where I have shown two streams going inside the control volume and one stream going out. Now if the flow is not a steady flow process, it is quite possible, like it will be dmcv by dt would not be equal to 0 if the process is not at steady state. But if the process is at steady state, this will be equal to 0, and I can say that m1 plus m2 equals to m3. So we'll start with the a generalized expression, that is the process is not at steady state, and we write this: the changes in mass of the control volume with respect to time is denoted to changes in the flow rate. So m3 dot is nothing but the rate of mass of the stream 3 minus m1 dot minus m2 dot. If this is at a steady state, this will be 0, this term will be 0, and dmcv by dt would also be equal to 0. And we can write that like this: dm, like m dot, can be converted to density, which is kg per meter cube, into velocity, which is meter per second, into area, which is nothing but the meter square. So if the area is constant, if the velocity and density are also constant, we can convert this into this form, and we can write that this is nothing but the mass flow. So this is a classical equation for a steady flow. Delta rho ua for a steady flow is equals to 0. So this will give you the numerical values of m1, m2 or m3, which is not known to you, and this can help you to calculate or to make further energy balance equation properly. So after this we go to the energy balance equation. So if you write a general energy balance equation, there is a similar control volume which I have shown with a different there is the same control volume, however the shape is different. You have flow in, flow out, right? We add some amount of energy and there is some amount of work which is being done on the system. Now dot represent the rate of that is energy per mass, work or work per mass, and there is a flowing system which is going in, going out. Okay, so if I write equation for that, right, the rate of change of energy in control volume is the net rate of energy transfer into the control volume. So if it is at a steady flow process, that also will be equal to 0. So energy associated with the flow are internal energy, kinetic energy, and potential energy, which can be written as this: internal energy, kinetic energy, potential energy per mass. So if it is this is to be written, this is per kg, per kg, per kg. If I multiply them with m, it becomes total energy. So net energy transferred by each flowing stream would be this. So when I multiply it with m dot, that is the rate of mass going in, I get this is the total energy equation. Okay. Now so net energy transported into the system by flowing stream would be this, where this delta refers to in minus out. So if it is out minus in, this will be plus. If it is in minus out, it is minus. So delta refers to this energy associated with this two. So this is in, this is out, right? So that is the difference between them is nothing but the changes in energy here, right? So let us try to write the equations associated with that. So this is the energy within the control volume. Now the control volume energy is represented only by internal energy, reason being the changes in kinetic and potential energy for the control volume is almost negligible. So here we only consider internal energy. Whereas for the flowing system, we initially consider internal energy, kinetic energy and potential energy, plus the amount of energy going in and the work. Now work can be considered into multiple forms. So work can be flow work and the shaft work. The flow work is given by P delta V, that is every element which is going in, right, has to push the element which is here. So thereby it adds the work. So that is P delta V. And in the same way, when an element goes out, it also has to perform some work. So delta of that is nothing but the work change or work flow work changes. So delta PVM dot is this. So when I substitute that here, in place of Q dot, I write this plus shaft work. So this is shaft work and this is minus D delta PV is nothing but the flowing work. So this equation would be the first term plus Q dot plus work rate bifurcated into two terms, shaft work and flowing work. Again the delta refers to in minus out for the given process. So this becomes your generalized energy balance equation. We can see here that if we combine this term with this term, we can write this as a combinedly as enthalpy H. So if I combine this and this equation for the flowing system, I get this, right? So my changes in energy in the control volume is this plus Q dot plus W. Okay, so this can be further written as this going on the other side of the equality, making plus equals to this. Now this is a generalized energy balance equation for any flowing process. Now if I further simplify this, right, if I consider that there are no changes in kinetic and potential energy for the flowing system, that is for this system, so I can eliminate this and I can write this equation as this. Still I am not considering this to be a steady flow process. If this would have been a steady flow process, this term also would be 0. So for a steady flow process, so energy balance for a steady state flow process, this term would be 0 and my equation would be reducing to this. So this is a generalized equation for a steady flow process. And here if I neglect energy, that is kinetic and potential energy, the equation would become this. Right? Now, like I can eliminate this as well. However, for single entry, single exit, that is for the process like this, if it is a steady flow process, this and this would be same, and hence I can write this as, I can divide this with m dot on this side, and I have every term here which is per kg. So enthalpy per kg, energy, kinetic energy per kg, potential energy per kg, heat per kg and work per kg. So this becomes my generalized energy balance equation for a steady flow process in terms of per mass. So this, the unit of each term in this equation is energy plus mass. This refers to the energy balance equation for a steady flow process, right? Or you can say first law of thermodynamics for a steady flow process, and this can further be simplified by assuming or by neglecting potential and kinetic energy to be written as delta H equals to Q plus W S, which is nothing but the expression similar to delta U equals to, this is delta H and that delta U equals to Q plus W. So this is the energy balance equation or the first law of thermodynamics for a steady state flow process, and we'll be utilizing it solving some problem when we meet in the next video. Thank you.